No, you don't have to put on that part. Okay. So, you may be wondering, what the heck is this even used for? Why is this important for us to know? And why is that? How does it relate to trig? How it relates to trig is that you can actually get definite values of sine and cosine from a trig table. So do you kind of remember from Math 2 when you would do trig and you would do like the sine of 30 and then put that in your calculator and get a number? But you'd always end up having to round? Kind of, sort of. If you don't, that's okay. But anyway, you can actually get exact numbers for specific angles with the unit circle. So before we do that, let's discuss how to get the coordinate pairs given the certain angle. So the first one, negative 120. Remember what I said the other day, negative angles are possible in math because the negative sign doesn't dictate that it's a negative number, it dictates what? It dictates the direction of which you're going around the circle. So we automatically go around the circle counterclockwise. If you see a negative angle, you're going to go around the unit circle clockwise. So you're still going to start in the same spot, but now we're going to go clockwise 120 degrees. So look at the position of 120 degrees normally. Okay? It's about a whole quadrant and some change from the starting point. So a negative 120, do you guys think that would be in quadrant 4? Because that's the first quadrant we have counterclockwise. Would negative 120 be in this quadrant? No. Would it be in quadrant 3 though? Yes. Because normally 120 is in quadrant 2. And that's if we're going clockwise. So, which of these 3 points do you think is the equivalent to negative 120 degrees? 240. So 240 is the same as negative 120. So what's the coordinates at that point? Negative 1/2, negative square root 3 over 2. Now the next one, 495 degrees. What's wrong with 495 degrees? Circles only go to 360. So you can still do 495 degrees. You're just going to go around the circle twice, at least. So how do you think I can figure out what the true angle 495 is equivalent to? Subtract 360 from it. So if you subtract 360 degrees, because it's at least one full rotation and then some change. If I subtract 360 degrees, what is it? 135 degrees. Well, isn't 135 degrees on the unit circle? Yep. So what is the coordinate that's associated with 135? Negative square root 2 over 2 and the square root 2 over 2. Now the last two, those we can just reference the unit circle. So when the angle is pi over 3, so that's in radians, what's the coordinate? 1/2 square root of 3 over 2. So we would go to where pi over 3 is, which is the same thing as 60. It'd be right here. What's the coordinate for 3 pi over 2? 0, negative 1. It's the same as 270 degrees, and that coordinate is 0, negative 1. So that might be some of the questions you're asked. Guys, you should not be playing games on your computers. Now, go to page 13. So here's the actual connection with the unit circle to trigonometry. The unit circle actually forms most trigonometry that we know of. Okay, the unit circle is the basis of trigonometry, which is ironic because it's a circle, not what you would think to be a triangle. But we discovered yesterday that within the unit circle are several triangles. Remember how we did all the 30, 60, 90, and the 45, 45, 90 triangles within the unit circle? That is part of the unit circle. So in other words, you can make right triangles of any size within that circle, whether it lines up with the actual degrees in the unit circle or not. The degrees or the radians or whatever the points that are on the unit circle, we are just the most common because those are what we get when we use special right triangles. So for exercise 1, the definition of sine and cosine functions. Sine and cosine functions form the basis of trig. And you define them so that their definition is consistent with what you are already familiar with concerning right triangle trig. So in Math 2, the only thing you did with trig in Math 2 was right triangle trig. Meaning everything you did with it was dealing with right triangles. So the main thing that you did was SOHCAHTOA. Do you guys remember SOHCAHTOA a little bit? So SOHCAHTOA just dictates, or it's an acronym to help you remember the different trig ratios. So you have sine, cosine, and tangent. So that's the S, C, and T of SOHCAHTOA. And then the two letters next to each of those three letters are their ratio that you would set up based off of their reference angle. So for sine, it's opposite hypotenuse. For cosine, it's adjacent hypotenuse. For tangent, it's opposite adjacent. So they're saying that if you have some right triangle and you have some reference angle, we're going to call that theta. The sides in reference to that angle would be their opposite, hypotenuse, and adjacent. I always tell my Math 2 kids, the easiest ones to find are the opposites and the hypotenuse. Because the hypotenuse is always across from the what? The hypotenuse is always across from the 90-degree angle. So that's hypotenuse. The opposite side is always across from the reference angle or theta. So this would be opposites. And then adjacent is just the side we have left over. So if I was to write out all these trig functions, sine of theta would equal to opposite over hypotenuse. Cosine of theta is equal to adjacent over hypotenuse. And tangent of theta is equal to opposite over adjacent. Now, you used all three of those with right triangle trig. In this class, however, we want to focus strictly on the sine and the cosine. Tangent is kind of a formula of sine and cosine, but we're not going to get into that. That's more of a pre-cal thing. In this class, we only deal with sine and cosine functions. Okay? So you need to know that sine of theta is equal to opposite over hypotenuse. They also state it here. And you need to know that cosine is adjacent to hypotenuse. Now, here's the connection to the unit circle. Given the right triangle shown below, and this comes from the unit circle. So they have the unit circle, they just don't have anything marked. So remember, the unit circle states that the origin is its center, it's a radius of 1. With some angle theta, so it doesn't really matter the angle measure in this case, whether it's in radians, degrees, whatever. They want us to figure out an expression for sine of theta. So first off, what I tell my students is, here's their right triangle that they drew. And here's your reference angle. I tell my students, always label your sides opposite hypotenuse adjacent first before you do anything with the ratios. So look at what all three sides are currently labeled. Which side is my hypotenuse? The 1. Across from the 90 degrees, that's my hypotenuse. Which side is my opposite? Y, directly across from the theta. So that means which side is my adjacent? X. It's the only one left over. So we just said that sine of theta is equal to opposite over hypotenuse. So sine of theta is equal to opposite over hypotenuse. So if we replace the values that we have for our opposite hypotenuse into that ratio, sine of theta is equal to what? What's my opposite? What's labeled as my opposite? Y. Over, what's my hypotenuse? 1. Now, what is y divided by 1 equal to? Just y. So this is the same thing as sine of theta is equal to y. So in other words, whatever the y coordinate is, that's sine. Now we're going to do the same thing for cosine using the same triangle. So cosine of theta, we already said that cosine of theta is equal to adjacent over hypotenuse. That's the formula for it. So that means cosine of theta would be what? What I label as my adjacent? Which side? X over what? Okay, guys, all of you lift your heads up. Come on. I'm not doing the sleeping thing today. Over 1. So in other words, cosine of theta is equal to what? Just X. So that means the X value of the coordinates.
When we write that out, can we put X, or do you want us to write like cosine,
Cosine equals X. Because you'll see what that means in just a second, why that's important. All right. Now, that's what the big takeaway is. Sine of theta is equal to the y value of the coordinates. Cosine of theta is equal to the x value of the coordinates. Meaning, you can calculate sine of different angles or cosine of different angle measures, because that's what you would plug in for theta, an angle measure. And as long as it's on the unit circle, you can get an exact answer instead of a rounded one. Okay? So that's what they state right here. So the definition of sine and cosine functions is for the angle in standard position whose terminal rate passes through the point xy of the unit circle, sine of theta is equal to the y coordinates, cosine of theta is equal to the x coordinates. So that's why it's really important to memorize that unit circle, because I can guarantee you on the EOC, they're going to want you to give exact answers. Like they may flat out ask you, what is the sign of 30? And they want an exact answer. So what is the sign of 30? So what you do is on your unit circle, you're going to go to where 30 is. So you're going to go to where 30 is, and you're going to look at the point. What value of the point does sine come from? The y value. So what's the y value? 1/2. So the sine of 30 is 1/2. Let's check ourselves. So in your calculator, first off, before you do anything, we got to make sure your calculator's in degree mode because our angles are in degrees. They're given to us in degrees. So to do that, you're going to hit the mode key, which is to the right of that blue second key. And do you guys see like 3 lines down how it says radian degree? If degree is not the one that's highlighted, you use your arrow keys to scroll down until radian's blinking. Use the right arrow key until degree's blinking, and then hit enter to change it to degree mode. So if they present you with angles in degrees, you need to make sure your calculator's in degree mode. If they present you with angles in radians, you need to make sure your calculator's in radian mode. Does that make sense? So in math 2, when your teacher would tell you to switch to degree mode and you didn't know why, that's why. Because now we know that radians exist, and that's another way to read angles. But your calculator automatically, like if you reset your calculator, for example, it automatically goes back to radian mode. Okay. So to get out of that, just hit second and then the mode key again. And I'm going to type in the sine of 30. And we should get what when we hit enter? 1/2. Is 0.5 the same thing as 1/2? Yep. No, it's exactly. If I hit math, enter, 1/2. I was about to say. All right. Now, let's find out the sine of 240. So go to 240 on your unit circle, and we're looking at which coordinate value? The y value. So what's the y value of the coordinate at 240? Negative square root 3/2. Let's go back to our calculator. I want to type in sine of 240. Now, your calculator gives the exact answer, but they give it as a decimal. So let's see if we're right. So I'm going to type in negative second square root of 3, and then I'm going to divide it by 2. And I want to see if I get the exact same decimal that I got when I did sine of 240. And I did. So yeah, that's why the unit circle is important. It gives you those exact answers. Put the phones up. All right, cosine of 90. So we're going to go to 90. But cosine is which value of the point? The x. So what's the x value of the point? 0. Let's check it. If I type in cosine of 90, I should get 0, and I do. You guys understand how this is working? So you just got to know that cosine is the x value, sine is the y value. That's the biggest thing that you got to take away from that. Otherwise, you're just looking at your unit circle and grabbing that part of the point. Okay, so cosine of 180, without me telling you where to find it, it's -1. It's the x value of the point at 180. And you can always double check it in your calculator too. Okay, sine of 90, what is it? 1. It's the y value of the point at 90 degrees. Sine of 135, what is it? Square root 2 over 2. The y value of the point at 135. Cosine of 150, what is it? Negative square root of 3 over 2. It's the x value of the point at 150. And yes, you do need to include the negative part if it has negative. And then finally, cosine of 0 degrees. 1. All right. Now, we can also use it to find some other parts. So the terminal ray of angle alpha drawn standard position passes through the points negative 0.6, 0.8, which lies on the unit circle. So it's not an exact degree that's on the unit circle. So which of the following gives us the value of the sine of alpha? So they said that this point's on the unit circle at an angle of alpha. But we don't know what that angle is, and that's okay because at least we got the points. So what's the sine of alpha equal to? 0.8. We just want the y value of this point. So sine is always the y value of the point. Cosine is always the x. Think about it this way. What comes first in alphabetical order? X. But cosine or sine, which one will come first alphabetically? C. So think alphabetical order. Cosine will go with x because those two both come first alphabetically. Sine goes with y because that's next alphabetically. I mean, you were right. I was doing it both ways. So the answer is 0.8. It is also important to determine the sign, positive or negative, of each of the two basic trigonomic functions for an angle whose terminal ray lies in a given quadrant. Okay. So look at the four different quadrants. So remember, this is quadrant 1, 2, 3, and 4. So look at the points in quadrant 1. Will the sign of any value that falls in quadrant 1 be positive or negative? Positive, because the y values are always going to be positive in quadrant 1. What about cosine in quadrant 1? Still positive. Cosines in quadrant 1 of the x values, they're still positive. What about quadrant 2? Be careful. Sine value is the y's, so it'd be positive and then negative. So just remember, this is y, this is x. Okay, so they flip-flopped them on you. They did that on purpose. What about quadrant 3? Negative, negative. They both parts of the point would be negative. What about quadrant 4? Negative, positive. The y value would be negative. The x value would be positive. So let's say I asked you to find the sine of 50 degrees. We don't know what that number is because it's not on the unit circle, but will the value be positive or negative if I find the sine of 50 degrees? Positive, because which quadrant would it fall in? Quadrant 1. Because quadrant 1 goes from 0 degrees to 90 degrees. So anything between it would be positive, positive, point-wise. If I asked you to find the cosine of 310 degrees, so cosine 310 degrees, what would the value be, positive or negative? Positive. It's in quadrant 4. Okay. Now, The last thing is a very simple Pythagorean identity that comes from this. So Pythagorean theorem. So the other day, we talked about how the equation of the unit circle is x squared plus y squared equal to 1. And this is what we know as the Pythagorean identity. So what they did is, we know that cosine of theta is equal to x and sine of theta is equal to y. So what they did is they just replaced x and y with cosine and sine. So for any angle, theta, cosine of theta squared plus sine of theta squared is equal to 1. So if you square your cosine and you square your sine and you add them together, you get 1. So that would be how you calculate angles that don't, or not angles, sides that don't necessarily fall on the unit circle. So for angle alpha, where the terminal ray falls in the second quadrant, meaning that angle is going to be in the second quadrant, it is known that sine of A is equal to 3 over 5. We need to determine the value of cosine of A. So we're going to first set this up as a Pythagorean identity. So they're saying that cosine of theta squared plus sine of theta squared is equal to 1. Well, don't we already know what sine of theta is, or sine of alpha in this case? So I'm going to change the theta to alpha. It's pretty much the same thing. It doesn't matter what you mark for the angle. So cosine of alpha squared, sine of alpha squared. Well, don't we already know what sine of alpha is equal to? Yes, no. Yeah, it's equal to 3/5. Sine of alpha is equal to 3/5. So I have cosine of alpha squared plus 3/5 squared is equal to 1. Do me a favor, put 3/5 squared into your calculator and tell me what that is as a fraction. It's what? It's 9 over 25, yes. So I would have cosine of alpha squared plus 9 over 25 is equal to 1. So how do I solve for cosine of alpha squared? Or get cosine of alpha squared by itself? Subtract 9 over 25 from 1. So in your calculator, go ahead and do that. And I still want it as a fraction. So cosine of alpha squared is equal to what? It's what? 16 over 25. So my last step would be to do what? So how do I get cosine alpha by itself? I get rid of the square, in other words. Square root both sides. So that cancels out. I have cosine of alpha is equal to, put the square root of 16 over 25 in your calculator and then convert it to a fraction. It should go to a nice fraction. Four-fifths. Good. So the cosine of alpha is 4/5. But we're not done, because where did it say it falls into? The second quadrant. So since it falls into the second quadrant, is that cosine going to be positive or negative? It's going to be negative, because the x values in the second quadrant are negative always. So make sure you also put the negative sign if it needs to change to negative. And mathematically, it still works, because remember, technically the square root of any number is plus or minus that number. It can be the positive version or the negative version. Because if you square a negative number, you still get a positive number. Okay? So as a point, if I combine those two values as a point, what would the point be? So if that was a point xy, what would that be? What's the x? -4/5 and 3/5. That would be what the actual point is on the unit circle. Okay, last one for this section. An angle theta has a terminal ray that falls in the first quadrant, where cosine of theta is equal to 1/3, and they want us to determine sine of theta in simplest radical form. So, once again, we're going to use that Pythagorean identity. So cosine of theta squared plus sine of theta squared is equal to 1. And the reason we don't have to put 1 squared, because Pythagorean theorem, we know it's c squared, is because 1 squared, no matter how you dice, it's always going to be 1. So I'm going to take this 1/3 and plug it in for cosine of theta. So I have 1/3 squared plus sine of theta squared is equal to 1. So what's 1/3 squared? So put in your calculator, give me a fraction. 1/9. So I have 1/9 plus sine of theta squared is equal to 1. So how do I get sine of theta squared by itself on one side? Subtract the 1/9 to the other side. So if I subtract 1/9 as a fraction from the other side, what would that leave me with? So I have sine of theta squared. And then what's 1 minus 1/9? 8/9. And then finally, to get the fraction by itself, or the sine of theta by itself, what do I have to do? Square root both. Now, this will not turn into a pretty number, but they want it in simplest radical form. So remember, you can take a radical. If you're doing a square root of a fraction, you can change that into the square root of the numerator over the square root of the denominator. It's the exact same thing. Those two expressions are equal. That's just a math rule that you can do. Now, we know the square root of 8 won't simplify, but what's the square root of 9? 3. So this is the square root of 8 over 3. Now, if we want to go a step further and actually simplify the square root of 8 radical, so let's see if you guys do it. So we need a perfect square to take out. So what's a factor? So what are two factors of 8 and of 8 where one of them is a perfect square that's not 1? 4 and 2. So I can rewrite this as the square root of 4 times the square root of 2, which I can rewrite as the square root of 4 times the square root of 2. So this is equal to, what's the square root of 4? 2 square root of 2 all over 3. So sine of theta in this case is equal to, you can either put the square root of 8 over 3, or it's equal to 2 square root 2 over 3. These two numbers are equivalent. You put them in your calculator, you'll get the exact same decimal. Now, it said it lies in the first quadrant. So do I leave it positive or do I need to change it to negative?
Positive.
Stays positive. That y value in the first quadrant is always positive. Any questions? All right. So that's it for this leg of the lesson today. We're not done though. We're going to do one last little thing. Okay. I'm going to go ahead and introduce the 8.4. Okay. So before that, we're going to do a little activity. So take out that other paper that I had you guys grab at the front. So it's the one that looks like a graph. So we're going to do some quick modeling real quick. Okay. You may want two different colors for this because you're going to have two different graphs. So this graph represents the number of daylight hours you have on each month in two different cities. The first one being Morehead City, the second one being Seattle. Okay. Miss Sherman made this and she's from Seattle. So that's why the other one's Seattle. Okay. Now, your month is going to be your X value. So over here, this is your X value. And your two daylight hours based off the city is going to be your two Y values. So you're going to have two different graphs. Okay. So we're going to call this one Y1 and this one Y2. So here's what I want you to do. I want you guys to graph the graph for Morehead City first. Okay, so here, I'll do a couple of points as an example with you. So if December, before the new year starts, December is 0. So how many daylight hours do you have in December? 10.3. So I'm going to come to 0. I'm going to go up to 10. I'm just going to go slightly past 10 to be the 0.3. So it's a little bit of guesstimate. It doesn't have to be perfect. All right. For January, the X value would be 1 because that's the first month of the year. Y value is 10.6 for Morehead. So I'll go to 1 and then 10.6. So I'm going to go to 10 and then slightly higher than the 0.3. So make sure it's slightly higher than the 0.3. For February, it's 2. And then for Morehead, it's 11.4. So I'm going to go up to 11, which is that middle line in between 10 and 12. And I'm going to go slightly higher, almost to halfway between 11 and 12, but not quite. And I put it on the line. It'll go here. So be careful. Each point should have a line in between them, vertical line in between them. For 3, 12.4. So I'm going to go all the way up to 12. And it's 12.4, so I'm going to go just a little bit under halfway to the next line. For April, which is month 4, it is 13.5, so I'm going to go all the way up to the line in between 13 and in between 12 and 14. That represents 13, and it's 13 and a half, so I'm going to get as close to halfway as I can between the 13 line and the 14 line. Again, it doesn't have to be perfect. You're just kind of guesstimating these points. For 0.5, it's 14.5. So I'm going to go all the way up to 14. I'm going to go about halfway between 14 and the next line. Then for June, it's 14.9. So I'm going to go to 6 because that's the 6th month of the year. I'm going to go all the way up to 14. And I'm just going to go at least like almost on top of the 15 line, but not quite. So as close as you can to the 15 line, just not quite on it. 14.9 is like a breath away from 15. So for July, the Y value is 14.7 in Moorhead, so 14.7 hours of daylight. So I'm going to go up to 14 again, and I'm just going to be slightly lower than my previous point. So I'm just going to do slightly lower than my previous points. The next one is August, so that's 8 to 13.8. So I'm going to go up to 12, and I'm going to go up one more line because it's halfway between. It's halfway between 13 is halfway between 12 and 14, so it's that middle line between them.
When we're done, do you want us to draw a line through it or no?
Yes,
Yeah.
you're going to connect it.
Okay.
And since it's 13.8, you're going to get pretty darn close to 14, but not quite on it. September, it's 12.8, so I'm going to go to 9. I'm going to go to 12. And I'm going to get, since it's 12.8, I'm going to get as close as I can to the next line up. So not quite on 13, but pretty darn close. For October, 11.7. So I'm going to go up to 10 first. And I'm going to go to the next line up from 10 because it's halfway between 10 and 12. And it was 11.7. So I'm going to get a little past halfway past 11. November is 10.8. So I'm going to go up to the 10 line. And then I'm going to get as close as I can to the 11 line without actually hitting it, because it's pretty darn close to it. And then finally, we end up back at December. So that means we should have the same number of daylights that we did in the first December. So that'll be 10.3. So try your best to level that point with the first point that you did. Doesn't have to be exact, but just close. And then you're going to connect the line.
That's what we do in Seattle.
Yep. So we did Moorhead together. So now I want you guys to do Seattle on your own. So go ahead, take a minute. So this is Moorhead City. Take a minute. I recommend doing it in a different color and graph Seattle on your own. So you're still using the same X values, the same months, but be careful. If you need to mark out the Moorhead one so it doesn't confuse you, because we did those together, you need to use the Seattle ones as your Y values. Okay, so take a minute. I'll give you guys about 5 or 6 minutes. Go ahead and graph what the daylight hour graph will look like for Seattle. And again, your points don't have to be perfectly exact. You just got to get relatively close to the actual number. Yes, sir. Sir. All right, guys. So you're graphing Seattle. Come on. So once you finish plotting all your points, make sure you draw a line through it. It looks like most of you are wrapping up your graph. So your Seattle graph should look something like this. Doesn't have to be close, or as long as it's close to that, it's going to be a little bit higher than the Moorhead one. And it goes a little bit lower. Now, here's my question. Why did I even bother making you do this? This is why I bothered making you do this. What type of function do you think, if I put a function to both of these graphs, what type of function do you think would describe it? So like the ones we know, like quadratic, logarithmic, linear, cubic, polynomial, radical. What do you guys think? What does it look like to you guys? It looks like it's quadratic. But what's kind of the issue? What's true about a quadratic? It keeps going down. So if you were to draw a quadratic, it would keep going down on both ends. But given kind of the pattern here, what do you think is going to happen if we say put another year?
It's going to go back up and then go back down again.
Right, it's going to go back up. So if we did another year, it would go back up and then back down again. Do we have a graph that's like, do we have a function yet that does that? So is there a function, so a polynomial function maybe that does that?
That's insane.
Are you sure? Because most polynomial functions, this is a quartic, still goes all the way down. And keeps going down forever.
No, I'm pretty sure it's
It's actually not. So, this is a brand new type of function that you guys haven't seen before.
Oh, how is that true?
But that's why I brought it up. Okay, we need a type of function to define what's going on with these two graphs. So that's what our unit circle comes into play. So let's see what happens with the unit circle. So I got something cool to show you guys. Okay, so I have a unit circle. This is a unit circle. It has a radius of 1, and the angles are just going around the angles. Now, I'm going to click a button. And it's going to create a graph. And the unit circle is creating that graph. This is a sine graph. So a sine function. So remember how we said that we were doing like the sine is the y value and everything? This is if we actually put in like sine of x into your calculator or into a graphing calculator. Your unit circle is actually creating your sine function. And isn't it that like kind of wavy looking graph? Yeah. Now, let's do cosine. Here's my cosine function. The unit circle's still creating it. It's kind of going the opposite way a little bit. All right. Now, how many times is it going around the unit circle before it starts over? So watch it again. How many times is it going around the unit circle before it starts over? Still going though. Goes around it twice. Just twice. Now, if I turn the sign on with the cosine, look at how it overlaps. So they're very, very close to each other, but they're slightly off, just a little bit. But couldn't we say that if we say shifted the sine function a little bit, couldn't it like be exactly the cosine function? Yeah. So sine and cosine functions are wave-like functions. If you like, the sine and cosine graphs are wave-like functions. So we use this a lot to describe, say, any type of data that will keep going up and down. So like years. Heart rate too. Heart rate can be described with it. What else could be described by a sine and cosine function?
Maybe.
Think about something in science that looks like a wave.
Oh, that one. Oh, she said it. I think she said it.
Say it again. Electromagnetic waves. I mean, yeah, that'll work. I'm thinking about something a little bit more simple.
Electronic. The sound waves.
Sound waves. Yeah. So that could also describe sound waves too. All right. So that is our new function. So the last thing we're going to do today is we're just going to figure out what the parent function of sine and cosine functions look like. Okay. So go back to your notes. So back to your packet, and we're going to go to page 17. So we're just going to do this one page. So we're just going to do this one page, and we're just going to figure out what sine and cosine and everything is. Okay. So we're going to make a table first for cosine of x and sine of x are your x values. So cosine of x and sine of x are your f of x. So we have f of x is equal to sine of x, g of x is equal to cosine of x. Our x values. Look at your x values. What do they look like to you? What do you recognize about the x values? They are radians. Uh-huh. So your x values are in radians. So in other words, they're angles. Your x values are angles. So we're going to do pretty much exactly what we did earlier. Okay? What coordinate is cosine of x? So what part of the coordinate on the unit circle is cosine of x? X. So cosine of x is the x values of the coordinates. Sine of x is the y values of the coordinates. So in other words, for example, we're going to skip the negative part for right now, but I'm just going to start at 0. If I did cosine of 0, so I plug 0 in for x. So my angle degree is 0 radians. So look on your unit circle where 0 radians is. What is the value at cosine? 1. If I did sine of 0, that one's 0. That's the y value of the coordinate at 0 radians. Now, pi over 2. So pi over 2 is the same thing as what in degrees? Where's pi over 2? It's the same as 90. So that doesn't really matter anyway, but just know that that's where you'll be looking. So what would be the cosine of pi over 2? 0. So the cosine of pi over 2 is 0. What about the sine of pi over 2? 1. All right. So we're going to keep doing it. What's cosine of pi? So go look where the pi is on the unit circle. What's the x value of that?
-1.
It's -1. What about sine of pi? 0. Cosine of 3 pi over 2. What would that be? So find where 3 pi over 2 is on the unit circle. It's going to be 0. And then sine. Whoa, what the heck? Sorry, my brightness just went down. So sine of 3 pi over 2 would be -1. Good. Then finally, cosine of 2 pi would be what? We're back at 1. So that means sine of 2 pi, we're back at what? 0. Now for the negatives, okay? Remember, negative angles just mean instead of going around counterclockwise, we're going around clockwise. So if I do negative pi over 2, okay, if I start at 0, pi over 2 is usually 90 degrees away going counterclockwise. So negative pi over 2 would be here. So it'd be the same thing as 270 degrees if we go clockwise. So what would be the cosine of negative pi over 2? Still 0. What'll be the sine of negative pi over 2? -1. Okay. Now, guys, if you wanted to do this in your calculator to check, all you got to do is first just make sure you put it back into radian mode. So hit mode and then scroll down with your arrows, have radian, click enter to switch it back to radian mode. Second mode to get out of it. If I did cosine of negative, that's not negative, that's a minus, negative pi divided by 2, still get 0. Okay. What about the cosine of negative pi? So that's, we know pi is 180 degrees counterclockwise, so it should also be 180 degrees clockwise. So what's the cosine? Not 1, -1. What's the sine? 0. -3 pi over 2. We know that is 270 degrees away from 0 counterclockwise. So if we go 270 degrees away clockwise, what would that be? So for cosine it'd be 0, for sine it'd be 1. And then finally, -2 pi. We'll probably just end up right back where we started, a full 360 degrees. So what is it? So 1 and 0. Because -2 pi will be right where 2 pi is. That's 360 degrees, no matter how you slice it. Now I'm just going to graph these points. So I'm going to do cosine first. So at -2 pi, I always tell my kids to start in the middle. So start on the y-axis. So I'm going to start with this at x equals 0. That's where I'm going to start. So at x equals 0, cosine is 1. Then pi over 2 is 0. Pi is, oh, that's not 1. This is 1. Pi is -1. 3 pi over 2 is 0. 2 pi is 1 again. Then if I go backwards, so I'm back at 0 again. Negative pi over 2 is 0. Negative pi is -1. Negative 3 pi over 2 is back at 0. And then -2 pi is at 1. So my cosine graph, and remember, it will keep going up and down forever and ever. So I'm going to make sure that my graph looks like it's going to go back down again. It will look like this. So this is what the parent function of cosine looks like. I'm going to do the same thing for my sine. So I'm going to start at the y-axis again. So I'm going to start at x equals 0. So when x is 0, y is 0. Then it goes to 1, 0, -1, 0. If I go backwards, it'll be -1, 0, 1, 0. So my graph will look something like this. So this is my sine of x graph. So they look very, very similar, but there are some slight differences. We're going to talk about those differences tomorrow. Okay, but now you know what their parent functions look like. These are both the parent functions of their respective graphs. Alrighty, so here's what I want you guys to do. I'm going to give you I'm going to give you 5 minutes to look at your unit circle. So I need everyone to wake up because you're about to take your unit circle quiz. If your buddy is sleeping in front of you, wake them up. Okay. Yeah. We'll see. So I'm going to give you about 5 minutes to study your unit circle. If you want to grab one and fill it in, that's fine, just for practice. I'm going to give you 5 minutes to look at it, and then we're going to do your first unit circle quiz from memory.